All right, let's look at a method to do partial fraction expansion when we have a repeated root in the denominator. If we look here at this function of s, we have a numerator that is some function of s that must be of an order less than that of the denominator. Our denominator has a root at negative b, s is equal to negative b, that has n repeated roots, and then it has, 1 through, it looks like j here, distinct roots. So the way that we'll do our partial fraction expansion for the distinct roots is the same as we've done them in the past, but when we have repeated roots we have to take a little bit of extra care. So if we look at how we've set up these, we've expanded the repeated root here from, if we have n repeated roots, we go from b naught over our s plus b to the power of n, b1, it's a beta 1, over s plus b to the n minus 1, all the way down, bn minus 1 finally to over s plus b. So if we have, for example, 7 repeated roots, we'll go from 0 to 6. So we're counting, our start of our count is at 0. Notice also how the numerator variables for our expanded function are defined. We have beta for all the repeated root numerators and alpha for the distinct root numerators. For the distinct root numerators, alpha 1 is over the denominator that has a root of negative a1. Alpha j is over the repeated numerator that has a distinct root of negative aj. However, for our repeated roots, they all are using the variable beta. The subscript 0 is over the repeated root to the power of n. So this is the first key thing that we need to know about expanding these repeated roots. Repeat them all the way up: 0, 1, 2, 3, 4, 5, up till n minus 1. So we can find that 0 root, the one that's under our beta 0, the one that is the numerator for our s plus b to the power of n. That can be found with the same method we've used before. So that beta 0 is just our s plus b to the power of n, that's the denominator, times our function g of s, where we evaluate that at s is equal to negative b. That's the root for our s plus b. The other terms where k is greater than, if we do beta sub k, where k is greater than 0, we have to make use of the derivative. So we'll call this the derivative twist. So if we have beta 1, for example here, beta sub 1, there we take 1 over 1 factorial, which is just 1, and we take the first derivative, but we still multiply our g of s here term by s plus b to the n. And same for if we have beta 2, over s plus b to the n minus 2, we take the second derivative, but we'd still multiply s plus b to the n, this original repeated root, times the function g of s. So let's look at an example here where we just have 3 repeated roots at s is equal to negative b. So our partial fraction expansion is to have, we expand that into the sum of 3 terms: beta 0 over s plus b to the power of 3, beta 1 over s plus b to the power of 2, and beta 2 over just s plus b to the power of 1, which will just say s plus b. So our beta 0 we can find the same way. We just will multiply all of g of s times s plus 3 cubed. When we do that, these are going to cancel, so we'll end up with a beta 0 here. Here we'll end up with just an s plus b to the 1, power of 1, that's a 1, and here we'll end up s plus b to the power of 2, but we're going to evaluate that at s is equal to negative b. So negative b, this will go to 0 and this will go to 0, and we'll just end up with our beta naught, or beta sub 0. For the second term, for beta sub 1, we're going to take the first derivative. So that first derivative, but we're still multiplying the entire function by s plus b cubed. So that whatever that n of s is, in this case, since we don't have our n of s, we'll just look at our expanded term over here, and the s plus b cubed, when we take the first derivative, sorry, first we have to multiply. So when we multiply, we'll do blue instead. These are going to cancel. So we'll take the first derivative of beta 0. Well, that's equal to 0. For our second term, we'll end up with s plus b to the 1. And for our third term, we'll end up with s plus b squared. So that's what we have to take a derivative of. For the first one, we'll end up with beta 1. Right, the derivative of that, with just derivative of s is 1. Here we'll end up with 2 s plus b, but we're going to evaluate again at s is equal to negative b. So when we plug in our negative b here, that term goes to 0, so we just end up with our beta 1. So that's how we can see why this works here. So if we then go ahead and look at our third term, b subscript 2, then we have to take the second derivative. So we go 1 over 2 factorial, so that gives us the 1/2, and we'll see we need that for when we take the derivative here. But again, we're multiplying by s plus b cubed, so that's going to go to, we're just going to be taking the second derivative of beta 0, that's 0. Here we're going to end up with a 1 there, and here we're going to end up with a squared, but now we're going to take the derivative again of s plus b. So we take that derivative, we end up with just beta 1. And our beta 1, we take the derivative of that, we end up with 0. We don't need the subscript 1 there. And we take the second derivative of this, we end up with 2 times s plus b. So that's why we need the 1/2 here to cancel out that 2, and we just end up with beta 2. So that's why this derivative twist works. So if we look at an example here where we have a voltage function that's 2 over s cubed plus 12s squared plus 36s, well, we can factor out the s, and then we can factor out s plus 6 times s plus 6, because we have s squared plus 12s plus 36. So we have s2 divided by s times s plus 6 to the power of 2. We have a pole at s is equal to 0, and we have 2 poles at s is equal to negative 6. We always want to know where are the poles of our function. So now we can set up to solve this problem with our method of residues, and we'll use our differential twist here, where we have beta 0 over s plus 6 squared and beta 1 over s plus 6 to the power of 1, and we have alpha, just some alpha over s, right? That's our distinct root. So we can evaluate alpha by multiplying our v of s by the root of the denominator of alpha, which is just s. So we'll do that. The s's cancel. And we'll evaluate it as s is equal to 0. So because we are evaluating at s is equal to 0, that's 0. So we just end up with 2 over 6 squared, or 1 over 18. So we want to continue to practice and get very good at distinct roots. Remember, we can also use the cover-up method. If we use the cover-up method, we can go up here to our original function. We can cover up. If we want to find alpha, we cover up the root s, so I'll just highlight it to show that it's covered up. It's no longer there. And then we'll evaluate it at s is equal to 0. That goes to 0, and we end up with a 1 over 18. So we can see that right here by using the cover-up method. That's for our distinct root. For our repeated roots now, we have to use, for beta 0, we can use the same method. We could still use the cover-up method for our repeated root. If we cover up this s plus 6 squared, and then we plug in for s the negative 6, we'll end up with the negative 1/3. This shows algebraically how we can write that out, but we can see it here quickly by practicing the cover-up method. So that system, again, we can do that the same way. It's the beta 1 that's new in this video. The beta 1, we have to take the first derivative. We take the first derivative, it's actually 1 over 1 factorial, but and there's a ds, we're taking the first derivative, but we still are multiplying by, even though we're finding beta 1, right, our beta 1 numerator is s plus 6, but we're still multiplying by the entire repeated root. So we're multiplying by the number of repeated roots, so we're squaring that. So when we do that, this cancels here, right? This is this entire function is down here. We're just using it on the left-hand side function to make it easier. And we're taking the first derivative of just 2 over s. So that first derivative of 2 over s is 1 over s is negative 1 over s squared, so we end up with negative 2 over s squared evaluated at s is equal to negative 6, and we end up with negative 1 over 18. So now we have all our, we have beta naught, beta 1, and alpha, and we have our voltage function in all these linearly separated, right? So we can use our Laplace transform table to take each of these inverse Laplace transforms. Here we have a ramp function multiplied by each of the negative 6t. Here we have just a unit step function multiplied by each of the negative 6t, and here we just have a unit step function. So we want to be able to access you should watch these videos with your Laplace transform table so you get good at using those. You know, we end up with that. We would end up with that function in time domain. But let's look here at a check that we can also use for a check when we're in frequency domain. Before we transfer, before we do our inverse Laplace transfer to time domain. And, so we can take this here, and if we multiply both sides, both sides of the equation by s over s plus 6 squared, then that should all equal 2. So when we do that, the s plus 6 squared, this is just going to end up with an s. Here we're going to end up with a s times s plus 6, and that's going to cancel. And here we're going to end up with our s plus 6 squared, right? So that must all equal 2. So we're just, multiplying out this denominator to prove that that's true. So we have negative 1/3 s. Here we have negative 1/18 s squared minus, that should be a minus 1/3 s, and then we have plus 1/18 times our s squared plus 18, oops, that should be 12s plus 36. Again, that's all got to equal 2. So we have our 1/18 s, negative 1/18 s squared, that cancels out with s1. Here we have 12 divided by 18 s. That doesn't, 12 divided by 18 gives us 2/3 s. Okay, that's the problem, because I missed in here. We still have this that's equal to, bring this down, negative 1/3 s. So yeah, the 12 divided by 18, that gives us 2/3 s, right? Pull the 18 here, and 36 divided by 18, that gives us a 2. So we do end up with 2 is equal to 2, and that's a check that we can use to cross multiply when we're using this method for residues. And then we do our inverse Laplace transform. We could rewrite this pulling out the u of t if we choose, and to format it a little bit differently. But here's our final result, and that's it for this video.